Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to see some case studies in deep neural networks and also learn about transfer learning and know why it is important to know about famous CNN architectures. So we will talk about AlexNet, VGG, GoogleNet, ResNet, and also we will see some of the ideas of these nets, but our main focus is on these networks and how could we use them to in our tasks. Okay, so the first network that we want to talk about it is AlexNet. So in AlexNet, as you could see, we at first layer we have relatively large filters. So we have 11 by 11 filters. We have stride 4 at the first layer, and we have some normalization layer that is different from batch normalization. So we don't want to talk about it, but because nowadays it is not used anymore. Instead of that, we use batch normalization, but in that time, in 2012, they used normalization layer. And let's see some of the important details of this network. So the first thing is that the AlexNet was the first neural network that used ReLU as the activation function. So, and it used norm layers, but not batch normalization. And it used data augmentation, so like image rotation and shifting the image and sharing that to in training time, as we talk about it. It used the dropout with probability of 0.5, and you could see other properties that network trained with, and maybe this is important one. So the learning rate was 1e minus 2. So at the first they used a learning rate 0.01, and to reduce the learning rate they used the value accuracy plateaus. So for validation accuracy they monitor the validation accuracy. So validation probably is something like this. So when they see some plateaus, means that we have a really very small improvements in the accuracy of validation. They decrease the learning rate to find the space more with more details. So in these regions, they, for example, from 0.01 they reduce the learning rate to 0.001 by factor, so by factor 10. Again, we had something like this, and so on. Okay, and they use the regularization in the neural network. And for using the regularization in Keras, maybe it is not bad to show to you guys how to use regularization layer in with Keras. So if you use convolution layer, so in Keras you could use the regularization both for convolutional layers and dense layers. So when you are building your model, one of the arguments are in fact is kernel regularizer that you could use to, for example, use L2 regularization in here. Okay, so when you are using and building your model, you could use the L2 with suitable factor in here. Okay, so now, and there is an example of how to use that. So this is L2 regularization with lambda of 0.01. Okay, we talked about it in the last function. Okay, let's move on. And if you see this double path, don't worry about it. The fact that these are actually the same network, but because in that time, in 2012, the graphics are the video cards are not were not very powerful, and they use in fact GTX 580 to train the model. So for this reason, they split the network into two networks. So they put half of the feature maps in one GPU and another half in another GPU to be able to just train the model more quickly. So don't worry about this, because nowadays we just put all of them in just one GPU, because the GPUs are really more powerful than that time. Okay. So as you could see in here, they are the first CNN-based winner in ILSVRC, or Image Large Scale Visual Recognition Challenge, and with 8 layers they bet the previous methods. So the error rate that they achieved is 16.4, so by 8 layers, so in 2012. After that, as you could see, deep learning models increased the accuracy or reduced the error rate in each year. Okay, so let's move on to 2013. So in that time, the ZFNet was proposed by some guys. So in fact, the ZFNet is like AlexNet. So it is actually like AlexNet, the architecture itself, but just with different parameters, like different convolution kernel sizes and different strides, and some different hyperparameters. So we don't need to so much inspect that. Okay. In the next year, in 2014, the VGG was proposed. Okay, in VGG we have 19 layers. Okay, so let's inspect that. Okay, so in VGG, instead of using large filters in first layer, so in AlexNet they used element by element filters for the first layers, but in VGG they use small filters, and also they use deeper networks. So instead of 8 layers in AlexNet, they use 16 and 19 layers. So as you could see, we have two famous VGG models, which is a VGG16 and VGG19, that related to the number of layers. And okay, let's move on to more important features. So why did they use smaller filters? So the fact is that if we use smaller filters, So they have, let's say, this receptive field in the image. So in the next layer, again, if we use a small filter, and this is related to this receptive field in this activation map, this could relate to a larger area receptive field for this small filter. So we don't need to use large filter in the first layers, because when we have an activation map, we could increase the number of layers, and by increasing number of layers in the next layers, we have the same receptive field in the input for those layers. Okay, so instead of using large kernel sizes, we could use more number of layers, but with a smaller number of kernel sizes. Okay, so they just use 3x3 kernels. Okay, so this is an analysis on memory usage and number of parameters of this network. So as you could see, let's go here, it is a better slide. So the most memory usage is in the early convolutional layers, because the image is large and we want to use 64 filters to the image. So the number of operations that we should use is a lot, but the number of parameters, as you could see in here, is not actually so much large. Instead, the most number of parameters are in fully conical layers. As you could see here, we have lots of parameters. In fact, approximately 100 million parameters for fully conical layers, okay, which is a lot in comparison with number of parameters in convolutional layers. And the total number of parameters in VGGNet is 138 million parameters, and it uses 96 megabyte for each image to from GPU RAM to actually process the image, which is somehow a little expensive. Okay. And so as you could see, they didn't use actually normalization layer, and they use ensemble of models to get the best results. So they actually trained different networks with same architecture, and then use the voting or ensemble the result to get the best result. Okay. So let's now move on to GoogleNet. Okay, so in GoogleNet we want to see what's the architecture. Okay, so GoogleNet has 22 layers, and in fact it is created by some sub networks, some very small networks. We call them module, or so they call them inception module. And as you could see, the GoogleNet has only 5 million parameters. So in VGGNet we had 138 million parameters, so it has just only 5 million parameters. And because in fact, it doesn't have fully connected layer except for classification. So in the last layer, we need 1000 fully connected layer because we have 1000 output classes. Okay, this is the number of classes that this dataset have, and so we need 1000 fully connected layer. But before that, like VGGNet and AlexNet, we don't have these fully connected layers. Okay. Okay, so in each inception module, they use a 1x1 convolution, 3x3 convolution, 5x5 convolution, and max pooling, and concatenate all of the resulting activation maps together to have the next layer result. But the problem with this is that when, in fact, the number of channels grows quickly, because when you concatenate them, you have 128 filters in here, 128 channels in here, 192 in there, and 96 in here, and so and some in here. So when you concatenate all of them, you are just adding all of those together. So when you are going to the next layer, this number of channels grow very quickly. So to solve this problem, we could use so you could see that we have 672 channels when we concatenate all of the channels. So to reduce this number of channels, we could use 1x1 filters, 1x1 convolutions to reduce the number of channels. So we use 1x1 convolutions to reduce number of channels from previous layer and apply the filters in the next layer. Okay, so this is in comparison with naive inception module. Okay, and we call those 1x1 convolutional bottleneck layers. Okay, so now instead of having 854 million operations for naive version, we just have 358 million operations for these network, because now we reduce the number of channels to 64 channels, as you could see in there, and now we just have 480 channels as the result. Okay, and as you could see, the next novelty in GoogleNet was these auxiliary outputs. So the problems with large networks or with deep networks is that when you use just this architecture, and when you use backpropagation, the gradient should flow from here to all of these layers. Okay, and when you have a very deep network, then the gradient will be very small in these layers, and so these layers are not very efficiently trained because of vanishing gradient that we talk about it. So to mitigate this problem in GoogleNet, we use some auxiliary branches to get the output, the same output as in here, to just inject some gradient from also these paths to the network. So now this layer, to update the weights in this layer, it gets the gradient from this branch and this branch and also this branch. Okay, now we could train the model more quickly and more efficiently. So they use auxiliary classification outputs to inject additional gradient to lower layers. Okay. And now you could see the summary of the points in here. Okay. After the GoogleNet in 2015, we had ResNet, which is in fact a revolution in the depth of deep neural networks. So AlexNet has 8 layers, VGGNet has 16 or 19 layers, and we have 22 layers for GoogleNet. But for ResNet we have 152 layers, which is a lot. But let's see how we could train this model and why this is so important to be able to train this model. In fact, in ResNet, we have this kind of short path to build the network. So we have 2 convolutional layers and 1 short path so we apply the convolutions, so we get some activation maps, and we concatenate these inputs also to the outputs of these activation maps and pass it to the next layer. Okay, so we are making a direct path from all of these layers to the output. Okay, we will see how this trick could improve the training and enable us to train such big network and deep network. Okay, so the problem in fact in plain networks or the networks without shortcuts is that there is a strange thing about that. So when we have 20 layers, when we train a 20 layers neural network, we could end up with this kind of training error. So this is a training error. When we increase the number of layers to, for example, 56, then if we plot the training, we could see that we have larger error in comparison with 20 layer neural network, which is strange, because we increase number of layers, we increase the number of the complexity of the function, but we don't get a better training error. And it is not actually related to overfitting, because at least we expect that this network with lots of complexity could achieve a really good training error, but it may be overfit. But the problem is not overfitting. Okay, the problem in fact is the optimization of this network. Okay, so when we have very large number of layers, then as I mentioned in the VGG, in the GoogleNet, we have the gradient vanishing problem. Okay, so the gradient from last layers in fact are barely get to the first layer, so we could not optimize the first layers efficiently, and so we end up with these plots, okay, which is worse than maybe shallower networks. So to solve this problem, ReLU used this kind of short path to alleviate this problem. How? Let's see. I think we have proof of that. Okay, so let's say we have a layer in the neural network. We could use the relation. So we know that we have this relation to the output of an input of layer and the next layer. Okay, so in a residual block, we import both the x of L and a function of that, which is maybe 2 convolutional layers. Okay, so in the L layer, we have this relation, right? So we just replacing this with this one and so on. Okay, now if we calculate the gradient of error with respect to the parameters of L layer, which is used in backpropagation, then if we use the chain rule, we could see that we have always this term, which is actually not a small number. Okay, so this is the gradient of last layer, and so it directly backpropagates to all of the layers. Okay, so if we have some residual block, the gradient could flow itself to even the first layer. Okay, so it directly backpropagates to the first layer plus some residuals. Okay, and this is this could actually make it unlikely to vanish, and in fact with this trick we could train more and deeper networks. Okay, let's see. Okay, so in ResNet also in fact we don't have fully connected extra fully connected layers in the ResNet, and also there are some versions of ResNet that worked on improvement of ResNet architecture by using one-by-one convolutions or bottlenecks. Okay, to reduce number of channels, and as you could see here, these are the properties that ResNet trained with. Okay, and as you could see in these plots, when we increase number of layers, so these are for without short path networks or plain networks. These are for ResNet architecture like networks. Okay, so with increasing number of layers, we are improving the network error rate. But in here, as you could see, with increasing number of layers, we don't gain any improvement. Okay. And as you could see, in fact, in 2015, ResNet won the challenge with 3.57 error rate. And this is a nice plot about the computational complexity and accuracy of the different neural networks. So as you could see in here, VGGs are a little computationally expensive for GPUs, and also actually you could compare different networks in here. And there are some improvement for ResNets. For example, you could use batch normalizations. In fact, it is for 2016 they used batch normalization and improved a single residual block to this architecture to get better accuracy. Okay. Okay. Now I want to actually talk about, I think there are also some other nets like stochastic depth net or squeeze net or fractal net. As you could see, they are really very new networks. This is for 2017 and so on, and you could see that now you could get the architecture and how it could perform. Okay, now all of these are some kind of tricks for better gradient flow. Okay, and also there are some networks that called SqueezeNet to reduce have a very few number of parameters, in fact, to reduce the computational complexity and size of the network. So, but now we want to know what is the benefit of knowing these networks, okay, and how could we use them. So the fact is that we could use transfer learning. So let's say when you want to train a neural network, a deep neural network, you probably need lots of training data, but probably for some tasks we don't have large data sets. So to train a network with small data sets, we could use transfer learning. So in transfer learning, we first train the network, for example, on ImageNet, or use ResNet, VGGNet that trained on ImageNet. Then when you have a small data set, then you freeze all of these weights in your pre-trained network and just retrain and fine-tune the last layer if you have a very small data set. If you have bigger data set, you could retrain more number of layers for these layers and freeze these layers and let these layers to act as feature extractor for your network, and we call this transfer learning. Okay, this is a nice table to explain transfer learning. So if you have similar data set, you could just use the last layer and so on. Okay, and also it is good to see how to use VGG or Inception or other nets in Keras. As you could see, Keras has lots of pre-trained network, so there are other architectures like Exception, which is different from Inception, and MobileNet, DenseNet, and another networks, ResNet, you could use as backbones or as the nets in here, and there are some examples that you could see how to use these networks in Keras. These are the most common deep neural networks that use in deep learning, and you could use them with your tasks. So you could actually set the weights when you write weights ImageNet, means that you want to use pre-trained ResNet. After that, you could retrain this network on your task, maybe your class is MNIST classification, so you just need to change the last layer. So instead of having 1000 output classes, you have just only 10 classes for different numbers for MNIST. But actually nobody for MNIST use ResNet because MNIST is very simple dataset, but just for example. Okay, so just change the last layer and retrain the network with these initial weights and freeze all of the lower layers. Okay, I hope that you enjoy from this session and from transfer learning, and hope to see you in the next session. Bye.